Okay, we are, tonight, there's a programming assignment 1 review. It's in the computer science building in the basement, in the X-Wing basement, so 050, from 6:15 to 8:15. And the TAs are running it. They're great. There's still a homework due. There's still a midterm. And today's plan is to talk about trees, rooted trees. And as a warm-up, here's the question for you. This is the warm-up question. What is the maximum number of nodes in a binary tree of height h? Binary tree has 2 children per node. What's the maximum number of nodes in that tree? I'll give you a minute. Okay, maximum number of nodes in a binary tree of height h. Let's look. Here we have a binary tree of height what? What height is this binary tree? No, this one right here. No, not 4. 3, number of edges. Number of edges on the longest path from the root to a leaf is the height of the tree. The number of edges is 3. This is height h equals 3. Quickly revise your answers. Now, how many nodes does this have? 15. So 15 when h equals 3. And can you put any more nodes into this thing? No. Yes. Sure, let's count the root. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. Okay, great. How did you think about this problem? I assume everybody's sort of like figured out what this is, but how do you think about this problem? I mean, what do you do first? You just solve it, like somehow magically? Yeah. What is the base case? Oh yeah, look at small instances, small examples. Very good. So I look at small examples. I say, well, suppose that I have something that has height. What does that have? Height 0. And it's got 1 node in it. So 0, h equals 0, and is 1. And now if I have something that has height 1, then I can keep adding things and I get something that has 3. And then I can do height 2 and height 2. I fill it up. And so this is like wasted time, right? Like at this point you're thinking, why am I drawing these pictures? The reason is because you're solving the problem. This is the way to do it, is you start with small examples and you look at them and you find a pattern. So here we are at this pattern. How many does it have? 7. Very good. Now you start to say to yourself, 1, 3, 7, 15. What do those numbers look like? Yeah, they look like they're about powers of 2. They look like almost powers of 2. Like if I just added 1 to them, they'd be 2, 4, 8, 16, and those are powers of 2. So this is really looking like something minus 1. Power of 2 minus 1. So then you think to yourself, well, let's see, what power of 2 would work? 2 to the h plus 1 minus 1. And you're reasonably happy. Or you might say there's 1 node at the first level, there's 2 nodes at the second level, there's 4 nodes at the next level, there's 8 nodes at the next level, and I can look at the sum of those powers of 2. 1 plus 2 plus 4 plus 8 is 15. And in general, if I sum up powers of 2 from I equals 0 to h, I will get, you know this because you're computer scientists, you add 1 to the binary representation of a number that's all ones, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. You add 1 to that, you have a carry. Carries all the way across, it turns into 1, 0, 0, 0, 0, 0, 0, 0, 0. So this is what we're doing here. We're adding, if I added 1 to this number, I would get 2 to the power h plus 1. So 2 to the h plus 1 minus 1 is what that sign is. Okay? This is our warm-up. Do you have any questions about the warm-up? So all along, I've been assuming you know what a tree is, but now let's define what trees are. Let's define what a restricted branching tree is. So it's a d-ary tree. Every node has at most d children. And so a binary tree is when d is equal to 2, and there's ternary trees, and there's quadrary trees, quintary trees. I don't know. Let's define them. And what they are, really, a tree, it's a recursive structure. It's got a root at the top, and then it has d children, and those d children are all basically d-ary trees. So at least one definition is we have a root with d-ary trees as children. Well, it has at most d children. At most d. So it's a root with at most d-ary trees as children. But I didn't write that because I'm going to be really sneaky. And there's the base case, which I'm going to let be an empty tree. The empty tree, or let's call the empty tree null. The empty tree, or a root, a node, along with d-ary trees as children. Now in this particular picture, this is a binary tree. I haven't shown the empty trees that are hanging off of these, but there's empty trees all over the place, right? These are all empty. This is a d-ary tree. According to our definition, it has a bunch of empty children all over the place. I didn't have to define it this way. I could have defined it as being a node is a d-ary tree, or a node with at most d children is a d-ary tree. Could have done that. But I decided to use the empty tree as the base, and I will regret this in the future, but we aren't there yet. So I haven't started regretting it. Any questions about this definition? A recursive definition. Recursive definition has to be founded on something. There has to be a base case. It has to sit down on some final say, and in our case, it's the empty tree. It's the final thing that you know, and the rest of it is all defined recursively. Okay. How many people are familiar with these recursive definitions of structure from 110? Not anymore? Holy cow. On so quickly. Okay. Right. So really what I should say here is that most D non-empty children. But usually when you talk about children, except in this definition, you talk about non-empty children. So even here, every node in a full D-ary tree has D or 0 non-empty children. So that's a full D-ary tree. It's like every node in it is full, or it's a leaf. Every node has got as many children as it could possibly have, or it's a leaf. So is this tree that I've drawn here, the A through L tree, is it a full D-ary tree? Yes? No? You're not participating? Okay, that's all right. No, it's not a D-ary tree because it has this node F, which is sitting around with one child, and that's not either full or a leaf. Okay, a perfect D-ary tree is a D-ary tree that has as many nodes as possible for its height. That's perfect. I don't know why, but bigger is better. So each level is full. Is this a perfect D-ary tree? No. Complete. You got all these categorizations. Actually, these things show up. That's the problem, is that we're going to see where complete trees show up. They're basically what you get when you're building a heap. Not like the memory heap, but a data structure called a heap. Those are complete D-ary trees. Perfect D-ary trees show up all the time. Full D-ary trees show up all the time as well. Complete D-ary tree means that every level of the tree is full. Every level has as many nodes as it could possibly have, except for the last level, and the last level is filled from the left. From the left implies that children are ordered. Like the children are numbered from left to right. You know, like you're from Italy and you name your children Primo and Secundo, and then it's that way. Your children are numbered in order. So if we look at this tree, is this tree a complete D-ary tree? Yes, every level is full except for the bottom level, and on the bottom level, all of the nodes appear shifted as far to the left as possible. If I had another node, like if I had a node here, no, not here, here. Oh, I don't know, K. I already have a K. M. Is that a complete D-ary tree? No, because there's a gap. Everybody good? Yes.
All those full D-ary trees essentially apply to all D-ary trees.
Is this a full D-ary tree? Is this tree written right there? Is that full D-ary tree?
I guess so, because everything. Oh no, because F is the exception.
Correct.
If I guess if L was pointing out the other branch, the F would really make a difference, right?
Oh, good question. If this was L, would this be a complete binary tree? No, it wouldn't. Because the direction of the arrows matter. This is what I mean by the tree needs to be ordered. There's a left child and there's a right child. And by moving the arrow that points to L by moving it to be a right arrow, what you told me is that L is the right child of the node F, and that F doesn't have a left child. And that means it doesn't satisfy my shift everything to as far to the left as possible. It's a great question. Yeah.
So just to clarify, it's perfect, then it has also complete.
Perfect means full and complete. Yeah. But in more. Yep.
We have J and K.
Oh, if I swapped J and K. Ooh. The labels on the nodes are just so that we can talk about them. The actual, it's sort of like the data that's being carried by the node is the number that I put on it, or the letter that I put on it. So really this definition is all about the structure of the tree, and so it doesn't matter. I could swap two children, make one the left child, one the right child in this particular, and it would still be a complete DRE tree because it's still the case that all of the nodes that are appearing at that level are shifted farthest to the left. They just don't happen to be in alphabetical order anymore. Yes?
I was wondering about node G. So, like, what's happening with node G? Does it have, like, two empty children?
It has empty children, so don't think of them as being children. Really. If you have an empty child, you don't have a child. I have lots of empty children. Oh, good. Excellent. I'm sorry. Maybe I come back to you ask
Yeah, I'll ask it.
something about G.
Yeah, I'll ask it.
Yep.
So I just want to confirm, like, a complete DRE tree means, like, there's no gaps on it.
A complete DRE tree. There's no gaps, but in addition, it's all shifted over to the left.
Yeah, so everything's on the left.
And then there are no gaps above it. It's perfect up to the last level, and then the last level is filled in from the left. And there's no gaps. Yep.
Or F and G.
Are F and G what? F and G children. F and G are not, they don't have all of their neighbors. I mean, they don't have all of their children.
They're not good.
What I mean by filled in is that the level is filled in. So if I look at this level, if I look at that level, and I look at, and I forget about this guy, and forget about the fact that I erased this guy, and I look at the nodes at that level has been filled in from left to right. If I look at this level, this up here, this entire thing has to be perfect in a complete tree. Perfect tree sitting on top of a filled in level. Yeah.
So you had just one node, but you technically consider that.
A full DRE tree?
Yes.
Yeah. Yeah. One node is just, it's full. It's got 0 or D children. In this case, it has 0. I'm glad you didn't ask me if an empty node, an empty tree is full. No, because I don't know. Sure. Okay, good. All right. The number of nodes in a perfect binary tree of height h. What is the height of a tree? Well, we know what it is. We just count the number of edges from the root to the deepest leaf in the tree, and that's the height of the tree. But we can also define it recursively, and we have a recursive definition of trees, and that kind of makes it useful. That recursive definition makes it useful for us to define height by using recursion. So how would you define this? How would you define the height of a tree recursively? This is something you should discuss. You should talk about it with your neighbor. And it shouldn't be that hard, except there's some weird cases. So I'll give you a minute to figure out the height, the recursive definition of height. Okay? Let's start with the easy part. What's the easy part of the definition of height? A recursive definition. Like, what's the height of a tree that's not empty or a single node? So what's that? What's the height of a tree that's not empty and it's not a single node? Height of T. Oh, no, I don't have to put it. So what is it? When I at least have one subtree. I'm the root, and I have at least somebody. What's my height? Yeah. So usually this is the case when you've got something that's got nodes in it. You got 1 plus the max over children C. Or maybe let's just say child C. Max over child C of the height of T C. And this, whoops. This is one of the trees, one of the child trees of the root. So this is the child's. Does it make sense? I'm looking for the longest path in the tree down to a leaf. So I want to find whichever one of these two trees is higher, this one or this one, will determine the height of the whole tree. So I take the max of those, and I add 1 because I have one step, one edge that connects down to my children. Okay, now, what is the base case for this recursive definition? Well, we know one thing, right? We know a height of a node, just one node, is equal to 0. Well, what is the height of the empty tree? Is it 0? Is it -1? Is it not defined? You can choose. You can choose. You choose 0? Okay. I'll tell you that in the future, when we talk about the height of the empty tree, sometimes it will be useful to define that as -1. So when we talk about balance in AVL trees, height of empty trees being -1 will be what we want. So anyway, whatever you'd like. Minus 1, 0, or not defined. I mean, you don't want to be ridiculous. Like infinity, you don't want that. But actually, does it matter? The only reason it would matter is whether you wanted to maximize over all of your children. Right now I've written maximize over all of the children of the root. Some of those children might be empty. In which case, it better be the case that I define this as being minus 1. But you could say, I didn't mean maximize over all the children, including the empty ones. I just meant maximize over the non-empty ones. So if you do that, then I don't care what you define the height of the empty tree to be, because you're never going to be using that. Do you see what I'm talking about? Okay. What is the number of nodes in a perfect tree of height h? We know what that is. Didn't we solve that as the warm-up exercise? But now we have a recursive definition of trees. Now we can actually prove something. So we have this, well, let's call it a conjecture, that the number of nodes in a perfect binary tree, that means in a full, it's completely, it's got as many nodes as you can put in there. So the maximum number of nodes in a binary tree of height h, that's what n of h is. And we know from the warm-up exercise that n of h is equal to 2 to the h plus 1 minus 1. But if we think about the recursive definition of the tree, we can come up with expression for this that is a recurrence relation for the number of nodes. So if I look at the number of nodes for a tree of height h, this is equal to, if h is large, it's equal to what? This is a perfect binary tree. It means it's just like it's got two equal children, like they're the same size. So what is the number of nodes in a tree of height, a perfect tree of height h, binary tree of height h? When there are children. I've got 1 for the root, and then I've got to count all of the nodes that are in here, and all of the nodes that are in here, and that's the number of nodes in a perfect tree of height h minus 1. What's the base case? What are the number of nodes in a perfect tree of height 0? 1. And now, from this recursive function that this recurrence relation that we've come up with for expressing that number of nodes, we can, and it comes from the definition. It comes from the definition of what a perfect tree is. It's a perfect tree is either a single node, or it's a binary tree that has a perfect left child and a perfect right child. And that's what this says. And so we can just see, is this going to solve to this? How do you determine that? How do you determine that? How do you determine that? Induction, thank you. Remember, you've only got the recurrence relation to work with. So if you want to prove something about it, you're going to have to use induction. And this is easy. This is a simple case of induction because we know the answer. And all we have to do is verify the answer. So what's the base case? The base case is when h is equal to 0. Let's check. Is when I plug in h equals to 0, then this number 1 should be equal to 2 to the 0 plus 1 minus 1, which indeed is 2 minus 1, which is 1. Yay. The base case holds. And then the inductive step here, or the inductive hypothesis, is that it's true for values of h smaller than h, or heights smaller than h. And we now want to show that it's true for height h. And so we just say, well, by the inductive hypothesis, that's IH for inductive hypothesis. By the inductive hypothesis, this is equal to 1 plus 2 times 2 to the h plus h minus 1 plus 1 minus 1. And that's equal to, let's go up here. And that's equal to what? Well, h minus 1 plus 1 is just h. So this is 2 to the h minus 1 times 2. So this is 1 plus 2 times 2 to the h minus 1. And that's 1 plus 2 to the h plus 1 minus 2, which is it's 2 to the h plus 1 minus 1, and that's exactly what we wanted. So it's easy. I guess what I'm trying to tell you is that don't be afraid to guess the answer to recurrence relations because it's so easy to check them. But don't forget to check them. Yeah.
So for like these induction proofs, so like, what's a good way to determine like how many base cases we demonstrate before stating the induction hypothesis?
Well, how many base cases should you use before you state the inductive hypothesis? This is a very good question. It actually is a good question for how many base cases do we need in the definition when we do a recursive definition. It's the same question. So I can just punt on this one and just say, well, the number of base cases that you use in your inductive proof is the same as the number of base cases in the recursive definition. But of course, then you might ask, well, how do I know how many base cases do I need in my recursive definition? This is a good question. It depends on the structure. Usually, for cases where you need more than one base case, there's some sort of change that happens, and then there's some sort of periodic behavior that repeats. In this particular case, we don't have that. But, I think it was important for us to have the base case for a tree with one node, and important to have the base case for the tree with no nodes, the empty tree. But you don't need the one with one node, because the one with one node is just exactly a tree that has only empty children. So you really only needed one base case, which was the empty tree for our definition. So you might be asking, why am I proving this for the tree with one node? This is where I regret defining it in terms of empty trees. It's a lot easier to think about the base case for height as being when there are height 0, as opposed to height minus 1. Any other question? Yeah.
So this induction proof is proving that the recurrence relation is equal to the
Correct.
So is it proving on both ways or just that way?
Both ways. It's an equality. But I don't exactly know what you mean by both ways.
Yeah, okay, so this is equal. I think if this, then instead in this case with
Who wants to talk about the height of an empty tree environment? Maybe we do. We can talk about it, but that's why I regret having to go to the base case of an empty tree for the sake of calculating height. I do not regret using the base case of an empty tree when defining a tree, because it sort of makes things simple. Somehow the definition, the recursive definition is simpler. Yeah.
Also, I guess if the phenomenon we're examining is a consistent behavior that doesn't change, maybe this is one base case.
Yeah, I mean, if you can define the process in terms of one base case, then you're good to go. But if you need more than that, then you are in trouble. So, like, you might want to think about, let's see. No, I can't say that. I'll think about it. I'll come up with something that requires 2 base cases, or maybe 3. Or right off the top of my head, I don't. Or not for trees. I thought maybe for, anyway, never mind. Any other questions? Okay. Ordered binary trees, they're just binary trees, but they're ordered. So that means that there's a left to right ordering on the children. And so I can talk about the definition as referring to the left and right ordered binary subtrees at a particular node. That's the only difference between unordered and ordered, is that you can change the order of the children in an unordered tree, but in an ordered tree you cannot. We are going to talk mostly about ordered trees. Why is that the case? Why in a data structures class would we talk about ordered binary trees more than just regular or old unordered binary trees? What do you think we're going to use these binary trees for? Doing stuff. What? Yeah.
Solving problems like the puzzle from like the cyber one and like for
For search.
like DFS and DFS.
Yeah, we could do it for search. I mean, the reason why I want these things to be ordered is because we're going to be looking at using these trees for doing search. So you're going to stash stuff in your tree, and you're going to want to look it up. And you'll start at the root, and you'll start looking down the tree to find the stuff that you've stored in the tree. And the opportunity is there for you to say, if my element is less than what's at the root, I'll go to the left. If it's greater than what's at the root, I'll go to the right. This is called a binary search tree, and this is one of the reasons why we want to look at ordered binary trees. Okay, but anyway, never mind. That's why we're looking at them. And how many empty trees hang on to an ordered binary tree with n nodes? You're counting this picture. That's bad. Draw with your pen a little picture so that you can count it more quickly. For 1, there's 2. For 2, there's 3. For 3, there's 4. Conjecture? N nodes, how many empties? Empties. Oops. Now check the big one, just to make sure you are correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, this looks good. Everybody happy? Proof complete? Does not work for n equals 0. When n equals 0, we have nothing, and we have one empty thing, just an empty thing. So it's 1. Yeah.
How would you want to
Good question. That's exactly what we're going to do. And you don't think I'd leave you hanging with that. But how would you do that? How would you prove this? What information do you have in order to prove this? What is the one thing that you have that you can use to prove this?
Say it louder.
A little louder. There you go. Induction. Because you have a recursive definition of a tree. This is a property on trees. It's an easy property to prove on empty trees. If I have an empty tree, then there's one empty and there's no nodes. And then we have a definition for what it is, what a tree is. The tree is now a node plus 2 children. So let's do that. This is the number of empties in, let me use a thing, n. En is the number of empties in a tree with n nodes. Notice that nodes, by the way, does not include empties. Empties are empties. Nodes are nodes. Nodes can be leaves or they can be internal nodes, but empties are just empty. Okay, so E of n is the number of empties in the tree. What is E of 0? Well, we have to ask ourselves, what is a tree with 0 nodes in it? But we know what that is by the definition of trees with no nodes in them. It's the empty tree, and that has 1 empty. So this is by definition of empty tree. From our recursive definition. And then what do we have? Well, we know that a given tree, any tree, is going to be, in this case is a binary tree, so we have an ordered binary tree. So we have 2 children, and we can say that the number of, so E of n is going to be the number of empties in the, let's call it the left tree, and the number of empties in the right tree, which are just the number of nodes in the left tree, E of that, plus the number of nodes in the right tree, E of that. But what property do we know about NL and NR? What is NL plus NR? This is, remember, NL, maybe I didn't tell you this because I didn't write it down, but I'm telling you now. NL is the number of nodes in the left tree, and R is the number of nodes in the right tree. It could be that NL is 0. If NL is 0, what is NR? If NL is 0, what is NR? N minus 1, because there's the root up here, and the total number of nodes in the entire tree is n. So we're using again the recursive definition, which says that a tree is a root plus children. 2 children in this case. So this is equal to n minus 1. In fact, it's always equal to n minus 1 because we always have that root up there, and the sum of the nodes in the other trees, sum of all the nodes in those 2 trees, is going to be n minus 1. So now, okay, great. Now we know that NL plus NR is n minus 1. And we have a guess that the solution to this recurrence relation is n plus 1. Let's see if that's right. Well, in the case when n is 0, it's right. In the case when n is not 0, when n is bigger than 0, we get that this, we're going to assume by the inductive hypothesis that the claim is true for trees with less than n nodes in them, and we're going to show that it's true for trees with n nodes in them. So what we can do is say, by the inductive hypothesis, I'll write it here, IH, this is equal to NL plus 1 plus N, plus NR plus 1, right? But what do we know? Well, we know we can rewrite that as NL plus NR plus 2, which is, well, NR plus NR, NL plus NR is n minus 1, so this is n plus 1. Right, this part here is n minus 1. So n minus 1 plus 2 is, so we're done. But we had to use the recursive definition of the tree. That's the thing that let us make these two statements.
I'm so sorry. Is it okay if you could perhaps rewrite FT and the definition?
Wait, which word can't you read?
Oh, no, FTs. Like right now I know what this sentence means, but just for future reference.
Oh, you want me to change empties to something else?
And with.
Oh, and with. Okay, great. You're welcome. Everybody good? Yeah.
So, the induction hypothesis is NL plus NR
No. The inductive hypothesis is the claim that we're trying to prove, which is that E of n is equal to n plus 1. It's that claim, but it's hypothesized for all values of n that are smaller than n, all number of nodes that's less than n, and then we want to show that it's true for number of nodes equals n. No, the fact that NL plus NR is equal to n minus 1, that comes from the definition of the tree. We know that the structure of the tree is a root plus two subtrees. So the number of nodes in that tree, in those two subtrees, is one less than the number of nodes in the entire tree.
We assume that E of n is n plus 1 for all n root is smaller than this.
Right. For all trees that have fewer than n nodes.
So we know NL is smaller than n.
Yeah, because the sum of NL and NR is n minus 1. So even if one of them is 0, the other one has one less node than the tree. Okay, great. I will see you on Friday.